All right, so now we move into lesson 7.3, absolute value equations part one. And we automatically want to start by recalling the piece of information that will be given to us on our formula sheet, which is the definition of an absolute value. The absolute value can be separated into two parts, separated by different domains, where we have our original x, which is our first piece, and we have our negative x, which is our second piece, and they're separated by the x-intercepts. Now, when we go on to solve these algebraically, essentially what we're going to be doing is just like the previous couple units where we said, hey, let's clearly define a type of equation or type of function, see what it looks like graphically, see how we can develop answers. What we want to now do is figure out specific x values in which these two would make this value true. Now, if we look at this in terms of solving absolute value equations algebraically, what we want to do is first and foremost, we want to isolate the absolute value equation. So wherever you see the absolute in the equation, make sure it's isolated. Then we want to consider two different cases. We want to consider where it's positive and where it's negative, or when it flips. Then we want to solve for specific x values individually and finally verify that they actually work in the original equation. Because again, if they don't work, then immediately what we want to do is make sure through that verification, we say they're extraneous roots or that they're not to be considered because they don't make the equation true. Now, let's see how we solve these things algebraically. Automatically, again, as a recall, we want to make sure that when we consider the absolute value equation, that whatever there was an input for x, it could have been a positive or negative, which means we need to consider two cases here. For the first one, what we're going to do is we're going to look at this and be like, part number one, when we solve it algebraically, I'm going to take the first root, which is the positive root. I'm going to isolate this for x, and when I isolate it for x, I'm going to subtract 6 from both sides, like so. This is going to give me negative x is equal to negative 4. And then from here, if I divide it by the negative, I would get x equals 4. Perfect. There's a first solution. Now, for my second part, I'm going to take that absolute value piece and I'm going to make it negative. So I take all of the same terms, but I surround them in brackets, put a negative on the outside. This is going to be equal to 2. I can divide the negative away, giving me 6 minus x is equal to negative 2. From here, I can subtract the 6 across, just like I did before, giving me negative x is equal to negative 8. And then when I divide the negative, I get x equals 8. Now, before I can confirm that either one of these is a solution, what I need to do is make sure I verify them, right? So I'm going to take this and plug them both back into the original. It's going to be 6 minus 4 absolute value is equal to 2. Well, that's the same as saying absolute of 2 is equal to 2, and this is definitely true. So we see 2 equals 2, left-hand side equals right-hand side. We can highlight x equals 4. We're happy with this. Okay, let's do the same thing with our other value. We take our 6 and we subtract our other value, which is 8. Absolute value equals 2. We get negative 2 as an absolute because 6 minus 8 is negative 2. Absolute of negative 2 is 2, so 2 equals 2. And if left-hand side equals right-hand side, these are both valid solutions, and we're happy with both of these. So again, we're going to solve for the positive root, the negative root, and then we're going to figure out, or I shouldn't say positive root or negative root, I should say the positive variant or the negative variant of the equation, and then solve for those x values. All right, let's amp up our difficulty just slightly. Now what we're going to do is we're going to add another term on the side of the absolute, and we know what to do with this. In step number one, we want to isolate our absolute. So I'm going to write this as absolute of 4x minus 5 is equal to 2 minus 9, because we're going to bring that 9 from our left-hand side here and bring it across to the right. 2 minus 9 is equal to negative 7. I'm then going to take the two variants of it. So I'm going to take the positive variant first, is equal to negative 7. I add the 5 across, I get 4x is equal to negative 2. I divide both sides by 4, and I get x is equal to negative 1/2, because 2 over 4 reduces to a half. Perfect. Okay, so we have one value. Our next piece here, we have to take the negative variant of it. So I'm just going to take from this equation here that we've set up, now that we've isolated that absolute value on the left-hand side, I'm going to write this as negative 4x minus 5. Remember, we take all of the same things and put a negative out front, is equal to negative 7. This gives us negative 4x plus 5 is equal to negative 7. I subtract 5, giving me negative 4x is equal to negative 12. I divide both sides by negative 4, and I end up getting that x is equal to positive 3. Okay, awesome. Now, let's just verify and see if either one of these works. So for step number 2, we're going to plug it in and be like, 4 times, let's take the negative 1/2 first, negative 1/2 minus 5, absolute plus 9, does this equal 2? Well, we're going to go down below here and be like, 4 times a half is negative 2, negative 2 minus 5, all absolute, plus 9 equals 2. This is the same as negative 7, and then plus 9 is equal to 2. Well, this is 7 plus 9 is equal to 2, and that's definitely not true. 16 does not equal positive 2. As soon as we see that this happens, we're like, oh, okay, let's go back to our equation, circle it, put a line through it, and write ext, extraneous, because it doesn't satisfy the equation. All right, now we need to do the same thing for our second value. We're going to do the absolute of 4 times positive 3. So I'm going to write in brackets, and let's just clean that up a little bit. There we go. Minus 5, absolute value, plus 9 is equal to negative 7. I write this as 12 minus 5. 12 minus 5 is the absolute of 7, plus 9 is equal to negative 7. And then this is going to give us 7 plus 9 is equal to negative 7. And that is where we have 16 is equal to, or does not equal to, sorry, negative 7. There we go. Perfect. And then I just want to make sure that this all makes sense on my other side here, because I had 2, 2, 2. On my other side of the equation, yes, I should have 2 for this side. My bad. Not negative 7, right? Because we're not putting in some other value. So for those of you that were like, wait a minute, where are we getting that from? Perfect. Okay, so here's our value. We're going to make sure we circle it, put a line through it, and write extraneous. There we go. I was probably thinking about the negative 7 from our equation here, but we want to plug it into the original and make sure that that's equal to our 2 there. So what does this mean? We're actually going to see very shortly what this means, but there's no solutions. You could theoretically write that right below here. Just say that there is no solutions. And that would be totally fine. Because if you can't find an x value that works, automatically then just no solutions. And again, graphically, we're going to see what this means in a second. All right, let's go on to part C and do a very, very similar process here. So for step number 1, we want to take this and consider the positive and negative. The absolute value is already alone, so we're going to write this as x plus 5 is equal to 4x minus 1. From here, I'm going to put the x's onto one side, the numbers onto the other. So maybe I bring the numbers here, and I bring the x's over to the other side, which means I'm subtracting an x and adding a 1 to the other side. I divide both sides by 3, and this is end up going to give me x equals 2. Okay. Now I take the negative variant. Negative x plus 5 is equal to 4x minus 1. I'm going to distribute the negative, making it negative x and negative 5 equals 4x minus 1. From here, I'm going to add the x over to the other side. I'm going to add the 1 over to the left-hand side. This gives me negative 4 is equal to 5x on the right. I divide both sides by 5, and I get x equals negative 4 over 5. Excellent. Okay, now we got to make sure we verify these, right? So let's do that below just because of the room we have available. Step number 2, we're going to say for the first one, 2, which is the x value, plus 5 absolute is equal to 4 times 2 minus 1. This is the same as the absolute of 7, which is equal to 8 minus 1. 8 minus 1, which is equal to 7. Yes, 7 equals 7. And as soon as we see that the left-hand side equals the right-hand side, go up and highlight that solution there. Perfect. All right, now we want to test our other point, right? So we're going to go back to the absolute. We're going to go absolute of negative 4 over 5 plus 5 absolute is equal to 4 times negative 4 over 5 and then minus 1. Perfect. Now I got to close the bracket there. Now, this is going to end up giving us positive 21 over 3, which is, or positive 21 over 5, my bad. We want to make sure we have the right denominator, which is equal to negative 21 over 5. And if this is a negative and a positive, well, clearly a negative doesn't equal a positive. So therefore, we need to write this as an extraneous solution because we see that it doesn't equal on the left-hand side and the right-hand side. As tempting as it is to say that that's a solution, it's not, because you can't have the negatives equal the positives. All right, perfect. Now, we've clearly seen a solution where we have 2 solutions. We have 4 and 8 for part A. For part B, we had no solutions. For part C, we had 1 solution. So you're probably thinking, like, what does this all mean graphically? Or like, what does this do for us? Well, here's what we're going to do in the next section. We're going to take a look and see when we plot these things out graphically, when do these situations apply? And like, how can we find this and verify this in our calculator? Now, again, what we're going to do is we're going to isolate our absolute values on the one side. We're going to graph that in our equation or graph that into our y1 and y2, find the intersection points, and then lastly, verify by checking it in your table of values or just making sure that you actually see that when you do your second trace intersect or your shift G solve intersect, you can actually find this thing here. Okay, in these first two examples, what good news is the absolute value is isolated here. Now, in this situation, when we look at this, we want to put our y1 as the first part, which is the absolute. So it's going to be 1/2 x minus 3 absolute. And I know my 3's are always terrible. There we go. And then we're going to put our number or whatever's on the right-hand side in our other part of the equation. Now, when we sketch this out, we want to have very particular window settings. So we're going to put -5 for x minimum, 16 for the maximum, and then our scale factor, we like to keep it as 1. We're going to write our minimum for y is -8, our maximum is 13, and then our scale factor is 1. Now, what this is going to do is it's going to give you a graph that roughly kind of resembles this here. So we're going to have this, and then I'm going to sketch in our y equals 4, which is roughly about here on the y-axis, which is equal to our y2. I'm going to sketch in our absolute, which is our 1/2 x minus 3, and this is going to cross something like this, go over here. Once it crosses and it hits the x-axis, we know it rebounds and it goes back this way. And then again, like if we were drawing this accurately, you know what we could do is we could put arrows in the end, but because these are going to extend infinitely and this is what our window would show us, we're okay with this. And now we just want to label those points. So one point is here where they intersect. The other point in which they intersect is here. So we have 1 point, 2 point, and if you use second trace intersect, you're going to find this is at -2 and +4, and you're going to find that this one is at 14 and 4. Now, what is one thing you notice about these is that they have the same y value, and that should be pretty obvious, right? We're saying some sort of absolute value crosses at this height in terms of verticality. They must share the same y value at that point. So hopefully that's okay. And again, you're using your second trace intersect or shift gsolve intersect on your Casio calculators in order to solve this. All right, let's look at this equation here. So we have this x plus 4 in absolutes, x minus 1. The absolute is already isolated, so we're going to write that in y1 as x plus 4. In our y2, we're going to write this as x minus 1. And if you need help entering the absolutes into your calculator, I can do that for you. On the TIs, first and foremost, you're going to click Math, click the right arrow to Number, and then click number 1, which is ABS, which is absolute values. On the Casios, you're going to want to click in your graphing menu, Option, Number, which is, I believe, F5, and then you're going to want to click ABS, all in capitals, which is your absolutes. But again, I can help you with that if you were struggling with getting those keys there. Now, again, I'm going to give you some very strict window settings. So I'm going to give you -15 for the x minimum, 6 for the max for x, and then 1 for the scale. We try to keep it at 1. I'm going to make this -8, 13, and +1 in terms of our window settings. So they look actually very similar to the last ones, just shifted a little bit left. Now, here's roughly what the graph is going to give you. It's going to have the x-axis here, or roughly about here, maybe a little bit higher. So I'm going to just backpedal that and put it a little bit higher. And then here's what the graph looks like. If we have the first part, which is our absolute, it's going to come down, touch the x-axis roughly about here. It's going to go through the y-axis and continue up about this way. In terms of my x minus 1, well, we know this is a linear graph with a slope of 1/1, and it's going to be down at a y-intercept of -1. And because it has this slope, it's going to look something like this. Now, if you realize both of these actually share the same slope, they're both linear lines. This is a 1/1 slope. This is a 1/1 slope. This one has a +4 y-intercept. This one has a -1 intercept. If they have a positive and negative y-intercept with the same slope, this gap between the two graphs will never close. They share the same slope, so they're increasing at the same rate. And therefore, we would say right away, there is no solutions because these things run parallel to each other. So we want to just write that as a note. They are parallel, or the lines are parallel. And thus, there is no solutions. Perfect. And we're going to make sure we highlight that here. So as soon as you see they have the same slope and they kind of resemble this, it's like no matter how much you adjusted your window, you could adjust your window such that it's like at positive infinity for x, you would see that those lines never cross. And so we want to be very specific with that. All right, let's go to a different graphic example, which kind of alludes to what we did on the first page. And it was if we have an example where they ask us for what specific values would make it so that we get certain solutions, well, let's just consider this first and foremost. What I want us to do is I want us to sketch out the graph that is due to the left-hand side here. So this left-hand side is going to resemble an equation. And remember, we can pull some specific information from here. we can figure out that the slope between any 2 points is 2 over 1, and that's given by our a value here. So let's just kind of like dissect this in terms of, we're going to pull apart the information. So our slope, which is equal to the a value, which is equal to -2. So we know that this thing in its original graph would have had some sort of like downwards facing graph or some sort of downward sloping graph. Now, for the next piece here is we want to pull out the information from the 1 and the 3. And the 1 and the 3, they tell us actually the p and the q, or they tell us a vertex value, a high point if you want to call it. In this situation, remember, whatever's in the brackets or whatever's in the absolute from this unit or quadratic functions, we always said our p was the opposite. So this is actually at -1, and it's at +3 for y, because the q value never got adjusted. Okay, so let's map this out here. Let's see if we can just provide the graph for this. I go over to the graph and I go, okay, well, my p and my q is at -1 and 3, so the high point is right here. And then in terms of using the slope to get the rest of the points, we go down 2 over 1, down 2 over 1, down 2 over 1 on the other side, down 2 over 1 on this side. And we just continue that pattern as long as it takes to get a specific set of points. Perfect. Now that we have our original graph, I want you to just draw a connecting line through it with arrows on the end. There we go. So here's our graph. Now what we're going to do is we're going to sketch in the following scenarios. They said what value of c would make it so that there is 2 solutions? Well, it's going to be any value that is going through this blue line and through both sets of blue lines at the same time. So let's just provide an example here. If I drew in green a line that was like this, a horizontal line, slope of 0 that goes through here. Well, this is for part A, so we're going to list this as over off on the side here, part A, and I should probably switch my tool here, part A. There we go. This occurs when y equals -1. Therefore, what values of c, for example, would make it so that there is 2 solutions? It must be anything strictly below the high point, or anything strictly below the red line that I'm drawing here. Because if it's strictly below, no matter which line I draw that's below and strictly below that highest point, you're always going to get 2 solutions. So what we're going to do here is we're going to say that our c value, which is equal to technically a y, must be less than the highest point. What is the highest point? It is 3, as long as it's any value below this. So I'm going to even state that as a sentence. Any value below 3. Perfect. Okay. Now, we want to talk about the situation where we have one solution. One solution means it intersects the blue graph one time and one time only. This occurs when it is exactly at the high point and crossing through what we want to call like the vertex point on these, or the maximum point. The maximum point, so this is for part B, this is where y is equal to, if we count it up, 3, it matches our vertex value. And so we go over here and we say the only place you get one solution is where the c is equal to a y value, which is directly equal to 3. So exactly 3. All right, now where we get no solution, we're going to go over to our graph here, and I'm just going to choose a different color. So maybe I use something like an orange. I'm going to draw an example of no solution. No solution occurs when it looks something like this one here. And you're probably thinking, okay, wait a minute. So now it's completely separated. It doesn't even like get near the blue line. And that's exactly the point. As long as we choose any y value that is strictly above that vertex, or that above that maximum point, we're going to get something where we have a line that never crosses the blue. And so in this situation, this is at, I think it's 1, 2, 3, 4, 5. Y equals 5 in this situation, which is above the blue line, and or the c value is 5, and that means it never crosses. But our summary is that we want to say it's for any c value which is technically equal to a y, which is strictly greater than the 3. And if it's strictly value, or if it's strictly greater, it will never cross more than, it won't even cross at all. So we just want to say any value above 3. Perfect. Awesome. Last example for this lesson, or this part of the lesson, is going to be dealing with an application which says, hey, we want to consider how absolutes can be dealt with in sentence form. So let's say we look at this problem. A computer process controls the amount of fish that are packaged at a specific size for a can. And they want to like program it such that it has a certain tolerance. The ideal mass that they want to accept is 170. So 170 would be like the perfect product. But the machine is programmed so that it can accept either plus minus 6 grams from that 170 that they're ideally trying to aim for. Solve for the absolute value equation and then figure out what this minimum and maximum are given for the mass of the fish of this size of can. Now, what we want to do is we want to right away be like, okay, in this situation, if m is the mass of the fish, if we want to call it that, we could use x if we really wanted to, because we're in this section where we might want to graph these things. So maybe I'll write it in both ways. Absolute value of the mass of the fish, which let's call it x just for a second, minus 170 should equal this 6. So if we take the mass of whatever this fish is and we subtract 170, which is that ideal mass, we should end up with the positive 6, because if we end up with that positive 6, we have the appropriate tolerance in here. Now, from here, I'm going to, again, write the equation in just a slightly different manner. So I'm just going to write it using m's instead. So I'm going to be like, the mass of the fish minus 170 absolute is equal to 6. These mean the same thing, but just to show you that you can write it using other variables. What we're going to do is, for part number 1, we want to solve for what is the maximum. So I'm going to take the one variant of the equation, which is the positive variant of the equation, and set it equal to 6. I add 170 to both sides, and I end up getting that 176 grams is our maximum. For step number 2, we want to solve for the minimum amount. I'm going to go the negative variant of this, so negative x minus 170 is equal to 6. I distribute the negative, making it negative x plus 170 is equal to 6. I then subtract the 170. This gives me negative x is equal to 6 minus 170, which is negative 164. I end up getting that x is equal to 164 grams. Perfect. So here's where we'd want to summarize it. Therefore, the maximum is 176 grams, and the minimum is 164 grams. Perfect. We would highlight this, we would take this as a solution, and we would find this completely acceptable here. Now, again, you would want to make sure that when you're thinking about these problems logically, I mean, like, you probably don't even have to write these as an absolute in your mind. You're probably like, oh, well, if I need a plus minus 6 grams, and it's from the ideal mass of 170, if I just add or subtract 6, I get my values of my maximum minimums. It might seem really obvious to you, but we want to make sure that we state it as an equation and then use those fundamentals that we've learned in this unit to be like, hey, we can derive the maximum and minimum based on an absolute, because it can give us that ability to go plus minus in each direction in an appropriate manner. Now, here's where you're going to want to go into your assignment. I definitely recommend trying some of these. There's even a show you know posted for this, so just make sure that you try out the show you know that is listed for this unit. All right, good luck with your practice.